So if you turn to page 468 or 467, you can add these notes off on the side. Maybe start on 467. And we're going to review a bunch of stuff from grade 11 just to set our context so that we're ready for grade 12 trigonometry. Okay? First of all, some definitions. Angles in standard position. Mathematicians always try to find, and scientists, a standard way of doing something so that when somebody says, I have an angle of 110 degrees, you're like, oh, 110 degrees is in quadrant 2. And everybody knows what quadrant 2 is, and everybody knows how to draw 110 degrees. So the first idea is an angle in standard position. We're going to draw a couple of them. I'm going to start with 110 degrees. That would look like this. I could draw an angle of 300 degrees. And I could even draw a negative angle of negative 50 degrees. All of these are in standard position. And so now we have to look at the key parts of the definition. The key part of the definition, number 1, the angle has to start on the positive x-axis. And if you go counterclockwise, that's positive. And clockwise is negative. So we got that negative 50, but the key thing for an angle in standard position is it is starting here on your x-axis, but not just any x-axis, it has to be the positive x-axis. So definition number 1. How do we measure an angle? Where does it start? Angles in standard position. Definition number 2. Maybe I'll scroll down instead. I think it's still. Definition number 2 that we're going to do reference angles. And I'm going to save some time, use the angles that we drew above to show you the reference angles. So we're going to I'm going to put a green box around reference angles, and I'm going to, on here, label reference angles. Those are the 3 reference angles for those 3 angles. So how do we define a reference angle? So a reference angle is a positive angle. It's always positive. So that's why I underline positive. Between the terminal arm is where the original angle ended. So terminal means to end. Where an angle ends, we call that the terminal arm of an angle. And so if we go between where the angle ends and the nearest x-axis, never y-axis. Although sometimes you'll be tempted to go to the y-axis because it'll go really close to the y-axis and you're like, ooh, maybe I should label this one. No. It is always back to the nearest x-axis. So even with 110 degrees, so if I go back up and look at the angles we labeled, come back again down. At 110, it's only 20 degrees away from your y-axis. It's closer to the y-axis. But your reference angle is always, always, always back to your nearest x-axis. And this allows us in grade 11 to do trigonometry for angles bigger than 90 degrees. In grade 10, you could only do trigonometry SOHCAHTOA with right angle triangles. And if you have a right angle triangle, all of the angles, except for the 90 degrees, have to be less than 90 degrees. There's no way you can draw a 90-degree triangle and have any of the other angles bigger than 90, because all the angles in a triangle add up to 180 degrees. So in grade 10, this is what your math looked like in grade 10. They were questions that said either solve for theta or solve for x. So if I had a 90-degree triangle and this was 50 degrees and this was x and this was 12, how would you solve for x? Okay, do you guys remember sine, cos, and tan? And we would use this to help us remember. So which one should I use, sine, cos, or tan, if I was solving for x here? Sine, because I have the angle, I know the opposite, I want to find the hypotenuse, so I would set up my sine ratio. And sine of 50 degrees would equal the opposite over the hypotenuse. And now we just do algebra. Go to our calculator. Maybe, there we go. 12 divided by sine of 50 degrees, and I get 15.6. Remember doing that in grade 10? And then you had questions where there was an angle. And again, you have to decide, am I going to set up my sine ratio, cos ratio, or tan ratio? I want to find theta. I know the opposite side, I know the adjacent side, so I would set up tan. (13/15), and you go to your calculator and you hit the tan inverse button to find the angle. And we get 40.9 degrees. That's a quick review of grade 10. It took a week in grade 10 to learn. Then in grade 11, they took away the triangles and just gave you the equation. They would say something like cos of theta is equal to -2/3. And theta was between 0 degrees and 360 degrees. So in grade 11, what happened is you needed to find a reference angle and you needed to use your cast rule. Do you remember the cast rule? It's called the cast rule because it spells cast. Right? I guess that sounds better than astica rule. Wouldn't work very good. Okay. So in the cast rule, for this question, we notice that cos is negative. And since it's negative, it has to be in quadrants 2 or 3. Because the cast rule is just a place to tell where your trig ratios were positive. The A says all of them are positive. The S says only sine is positive in quadrant 2. Tangent and cosine are going to be negative. And in 3, the T says only tangent is positive in quadrant 3. And sine and cosine need to be negative. And in quadrant 4, of course, only cos is positive. So what we have, when we have cos of theta is equal to negative 2/3, it's telling us that we have an angle either in quadrant 2 or an angle in quadrant 3. And in order for us to connect to grade 10 math, grade 10 math only works with right-angled triangles. We need to make a right-angled triangle, and we make that right-angled triangle always with our nearest x-axis because we have to use our reference. And if cos is adjacent over hypotenuse, we could label this length would be 2, this length would be 3. Same thing here. Now this length is 2, this length is 3. If you go back to grade 10 math, could you find that angle? Absolutely. Right? In grade 10 math, I could find my reference angle by doing cos inverse of 2/3. Notice I do not put the negative in. Number one mistake students do, they'll go to this, they'll do cos inverse of negative 2/3, they'll get an answer, they'll actually get one answer right and get the second answer wrong. Because watch what happens, I go to my calculator, okay? I need to get 2 answers. This is what students do, they go second cos inverse of negative 2 divided by 3, and they get 131.8, and they think this is their reference angle. Okay? Maybe we need to make sure we add another thing to our reference angle. If you're going to your nearest x-axis, it's going to be less than 90 degrees. There's no way you can go to the nearest x-axis and take more than 90 degrees to get there. Then you've obviously traveled too far. So the number one mistake from grade 11 is that when we find a reference angle, they get an angle too big. But if I would have done grade 10 math on this one and done, that's an actual triangle. Triangles have actual positive lengths. My reference angle is supposed to be 48.2 degrees. Then to find the actual angle, we are finding the angle in standard position. Because our answer was supposed to be between 0 and 360 degrees. Those are positive answers, so we're going in the counterclockwise direction. And now I know what my reference angle is. Can you see in this one, my actual angle would be 180 degrees all the way here, minus the 48.2 degrees. And in quadrant 3, my angle will be 180 degrees would get me halfway, and then I would have to add my reference. So my actual answer for this question is that theta is equal to, here we're going to get 131.8 degrees. And here we're going to get 228.2 degrees. And interesting on your calculator, that when you do cos inverse and negative 2/3, it does give you a right answer. 131.8 is a right answer. But it would not let you find the other answer. So we do have to always find our reference angle first. Okay? And in AP Calculus next year, for some of you, you will understand why cos inverse gives you an answer in quadrant 2, and why sine inverse and tan inverse give you negative answers in quadrant 4 when you put in negative values. But for right now, we're going to stick with our grade 11 math and say in grade 11 we learned our cast rule. The triangle got taken away, so then you had to think about where that angle could be according to your cast rule. You could draw it with your reference angle and always make a triangle back to the nearest x-axis. We are going to do that lots in grade 12 as well. So we get to redo all of this mathematics that we did in grade 11. We get to redo it again in grade 12. Some of the things that are different in grade 12 is grade 11 stopped at 360 degrees. Grade 12 says you can use any angle, positive or negative, forever. So then there's going to be more answers. And with that comes our first new definition for today, which is coterminal angles. Negative 135 degrees and 225 degrees end in the same spot. So we would say they're coterminal. Another example. (100 degrees and 460 degrees are coterminal because they end in the same spot. A nice application of this is you can think of like those fancy skiers that go down and do tricks up in the air, right? Sometimes they get to the jump and they spin around and they do a 360, right? And they land. They land as, if I was going down there, I would just be like, I would do a 0 degree. I'd be like up, oh, and hopefully just be able to land staying straight. I would not attempt to do the 360 because most likely I would hit another angle. Yeah, that would be bad, right? I'd probably do 90 degrees and get scared and be completely sideways and crash, right? 720 is even more impressive because they go twice around and they land in the same spot, okay? The key thing is they do have to land in the same spot and be coterminal with 0, otherwise they're going to crash. So 0 and 360 degrees and 720. Well, sometimes snowboarders, they do 1080s, don't they? 3 times around. Can they do 4? Has anyone done 4 in a competition?
I don't think in your competition Someone's probably done it off like a mountain or something.
Probably someone. So we have this idea of coterminal angles. And that's also, if you want to, in our notes on page 468, they talk about, we can highlight these ideas. We can talk about standard position. We had a positive angle in standard position. We have a negative angle in standard position. And the definition of coterminal is in our notes as well. So here they have three, 40, 400, and 760. And you could also go in the negative direction. 40, negative 320, negative 680. Does it make sense that 40 is 360 plus 40? Because if you are at 40 and you add one whole time around 360, you're going to get back exactly where you started. And if I add 360 twice, I'm going to get back to where I started. So finding coterminal angles is actually quite easy. You can always find a coterminal angle by taking the angle that you're at, and you can add or subtract 360 degrees as many times as you want, right? Would you agree that 3,640 degrees is coterminal with 40 degrees? How many 360s did I add? 10 of them, right? 10 times 360 is 3,600 plus the 40. That's going to end in the same place. It'll just go around and around and around and around. Does it make sense that there are an infinite amount of coterminal angles? And we can learn how to write this infinite amount. I'll highlight that here. This is how mathematicians come up with writing an infinite amount of answers. Okay? Because otherwise it's a problem. Write down all the coterminal angles, and you'd have to do that until you die, and you wouldn't finish, and you'd fail. You probably wouldn't even get half done if you had to write all of them. So mathematicians say, well, there's got to be a way that we can do this, and they do it this way. They say, start with 40 degrees. Then add 360 degrees any number of times. So they put a K, and they define K that notation right there. K belongs to the integers. The symbol Z there is integers. Integers are positive and negative whole numbers. Yes.
When you're trying to solve for them, you just substitute the 40 for
Whatever angle you're wanting to find all the coterminal ones,
yeah,
you can put there. Actually, it would be fine if you put 400 instead of 40. Because this says you have a starting spot. There's my starting spot. Any angle starting there. And then I need to add 360 or subtract 360 as many times as I want. And that will list them all. So when we say K is an integer, this means that K could be 1, 2, 3, 4, 5, or 0, or negative 1, 2, 3, 4, 5, and so on. So we could add 367 times. We could add 360 12 times. We could subtract 360 5 times, 8 times. All the numbers would be included. And this is something new for grade 12. We're going to get into this idea of general solutions. But we'll get to our first example. So in part A, we're going to draw an angle of 85 degrees in standard position. And we need to list all the angles that are coterminal between -800 and 800. So could we add 361s? If I added 361s, would you agree that that would be this one? And 360 plus 85 would be 445. So I'm going to start listing all of them. When you're listing all of them, you include the one that you started with. Because technically, if you drew another angle of 85, would it end in the same space as 85? Yes. 85 is coterminal with 85. In fact, they're the same. But the next one was 445 degrees. Can I add another one? I can add 360, but do you see that it just goes over? So I might even show it. If I add 360 again, that's 805 degrees. I'm going to put a line through it because I'm only supposed to go up to 800 degrees in this question. And now we have to subtract. If I subtract, what is this angle? Okay, I start with 85, I subtract 360 degrees. I'll write the negative ones here in with the negative value. You can see that you get negative 275 degrees. If you subtracted 360 degrees again, oh my goodness, it would look like that. So, what do we got? Negative 360, what's another negative 275? That one will be negative 635 degrees. And you might notice that you can't go any further. Our diagram is terribly messy. All those spirals, it's crazy. You know what? You probably didn't even notice, but while I drew those spirals, I hypnotized them. You guys are all currently in a state of hypnotic state. So I can make all sorts of suggestions, and you'll change your life. Little things like, after I bring you out, you're going to be like, oh, I like math. This is crazy. I want to do my math homework tonight. Okay? So I'm gonna snap my fingers. You're going to be pulled out of this hypnotic state, and you won't know why this change in your life happened, but it's going to be for the good. You ready? All right. We'll get to question B. Now we want to write an expression for all the angles. This is actually easier, because if you want to write the expression for all the angles, you just have to add or subtract 360 degrees as many times as you wanted, but we have to make sure that that is a whole number, either positive or negative, so we say that k belongs to the integers. Circle questions 4 and 5.